everybody. So today I'm going to tell you about, sort of as I hinted when I introduced myself on Monday, some interactions between a problem in Schubert calculus and studying its computational complexity. And to do that, I should probably tell you what each of those things are so that you care about anything. I'm going to start by giving very introductory crash course in complexity. So what is the class P? Okay, so these are the problems that you can actually decide if the answer to your question is yes or no in polynomial time. Okay, so for example, we could decide if a graph is two-colorable in polynomial time. Okay, you can sort of, if you get bored, you can think about what is a polynomial time algorithm to decide if a graph is two-colorable or equivalently bipartite. Okay, less obvious is primality, but you can actually decide if a number is a given integer is prime in polynomial time. And this is an example of a decision problem. So this is just the type of problem the type of answer that I want is just either yes or no. Okay, so what's one step up from that? We could look at NP. So this is non-deterministic polynomial time. And so what this is we want to check evidence of a yes answer in polynomial time. So what do I mean by that? I'll give an example, 3 coloring. So if I have a graph and I want to know, does there exist a 3 coloring of this graph, then you can just hand me a proposed 3 coloring, and in polynomial time, I can check that it follows the rule of a 3 coloring for my graph. Okay? And then a co-class is just doing the opposite, yes versus no. So this is checking evidence of no in polynomial time. So an example of a problem in here would be for integer factorization, does there exist a factor at least of a certain size of a given integer? Okay, so these are decision problems, and these are living in the polynomial hierarchy. So we have P at the bottom here, and we have that P is sitting inside of both NP and co-NP. And when we're trying to look higher in the hierarchy, there are much more complicated problems than these. And how we can look sort of one level up, this class, NP, where this exponent is NP, these are the problems that we can, what this NP is saying is we want to check evidence of yes in polynomial time, where we're allowed to call a very hard problem that's in NP in unit time. And so if we're allowed to sort of just make these cheats, these quick cheats of calling a hard problem in the next lower class in unit time, if with that extra power we could check evidence of yes in polynomial time, then we're here. And similarly, if we could check evidence of no, calling here in unit time, then we would be in this class. And so by building upwards, we get the whole polynomial hierarchy. Okay, so that's the general framework that we have. Well, I'll leave it up for a bit. Okay, so those were decision problems so far. But we're also going to be interested in counting problems. Where rather than wanting to get a yes or no answer out, I want an integer, a non-negative integer. Okay, and so the main problem that we're going to talk about for that is sharp P. And this is sort of, you can think, the counting version of NP. And so informally, what this is we want to be able to check evidence of a +1 to the cardinality of the set that we're trying to enumerate in polynomial time. And so an example here would be sharp 3 coloring. So how do I know that a given graph is contributing a +1 to the total number of 3 colorings of my graph? Okay, the same intuition there. Okay, any questions about our complexity crash course? Okay. And so now we'll get into the Schubert section, or Schubert motivation. And our general motivation is we want to study the intersection theory of Schubert varieties. And so these Schubert varieties, let's build them from the ground up. We'll start with the complete flag variety, which we can think of as a quotient of our n by n invertible matrices with complex valued entries, quotiented by, this is a Borel subgroup that's sitting inside of our GLN. That's going to consist of our upper triangular matrices here.
Sorry, with the previous section, I just had a question. If NP is co-NP, does that imply the polynomial hierarchy like collapses?
That implies a collapse. Okay, so for our complete flags, if you don't like this definition, you can also think of these as chains of subspaces, where I'll start with 0, and I'm going to have a one-dimensional subspace sitting inside of a two-dimensional subspace, going all the way up until Cn. Okay, so the complete flag variety is all of the chains of this type. And you can see that these are sort of in correspondence with these, where you can think of a matrix is telling you the flag by saying that the first column of the matrix is giving me the first vector that's generating V1. I add the second column to generate V2, and so on. Okay. And so in the complete flag variety, so this is our flag variety, we can study something called a Schubert cell. And we build the Schubert cells by taking orbits of the complete flag variety. So if we take the orbits, rather than taking the upper triangular matrices, we could take orbits of the lower triangular matrices to build Schubert cells, just like this. Okay, so we take our left and right cosets here, and we're quotienting by this Borel. Okay, we can again think of these rather explicitly as matrices, where this is our lower triangular matrices. And the Schubert variety is just the Zariski closure of the Schubert cell. Okay. And so I'll write this as XW. So we get these Schubert cells by taking these orbits, these B- orbits in the complete flag variety, and these orbits are going to naturally decompose in terms of permutations in the symmetric group. Okay, so these permutations are going to naturally index everything in the picture that we're discussing today. Okay, so we have our Schubert variety, and so our goal is to study the intersection theory here. And so what do I mean by that? I want to know, how can I compute the number of points in a generic, let's say, triple intersection of Schubert varieties? So how can I enumerate the number of points in, let's say, the intersection of XU, XV, and let's say that's G1 here, where G1 and G2 are random flags, such that if I wiggle the flags a little bit, the number that I get out isn't going to change. Okay, so we want a generic intersection here. Okay. And so the tool that we're going to use to be able to get a reliable computation of this intersection is cohomology. So what we want to study is the cohomology of the complete flag variety. And under this, we'll see that the Poincaré duals of our Schubert varieties, these are Schubert classes. And so these are going to be sitting inside the cohomology ring of the complete flag variety, and they'll give a Z basis for this cohomology ring. And so what this means rather explicitly is I can take the cup product of xu with xv, and that's going to expand back into this Schubert basis. Okay. And what we know, based on how we're formalizing this cohomology, is, in fact, this number and this number are going to be the same. Okay, so computing this product in cohomology is going to precisely compute this intersection number. Okay, I know that was probably a lot. Yes?
I'm a little confused. When you say that the G in the second line are in FLN, you mean, don't you mean like in the group, like in GLN?
They should be flags. We'll think of them as flags, but you can think of them as matrices. We're going to multiply the matrix representatives by whatever matrix. But they should be flags. Or I guess here, you can think of them as in GLN. I was doing some different conventions. Thank you. Any other questions? Okay. So cohomology is can be hard to get a handle on. And so wouldn't it be nice if we had a more concrete way to study this cup product? And so luckily, we know from the Borel presentation theorem that the cohomology ring of the complete flag variety is actually isomorphic to just a quotient of the polynomial ring, where what I'm quotienting by are the symmetric polynomials in n variables with no constant term. So equivalently, you could think of quotienting by all of our elementary symmetric polynomials in n variables. Okay? Another name for this is our coinvariant ring. That I know some of you are a fan of studying and generalizing. So we have this really concrete isomorphism. Okay. What's more is, let's think about what should our Schubert classes correspond to in terms of the world of this quotient. And so, of course, you can come up with lots of different representatives, but our favorite for this talk is the Schubert polynomials, as noted by Lascu and Schutzenberger in 1982. So this Borel presentation theorem is in 53. These were introduced in 82, so lots of time to come up with particularly nice representatives here. And so what this says is, maybe instead of trying to work in terms of multiplying in cohomology, let's study the problem of multiplying these polynomials. Okay, so why do we like Schubert polynomials? Maybe you don't. But why they're nice is they have a nice combinatorial, very explicit combinatorial expansion. Expansion into monomials. So just like our Schur polynomials, if you're familiar with Schur polynomials, expand very explicitly in terms of semi-standard Young tableau. And you can read off weights of these tableaux that tell you the monomials. And the same with Schubert polynomials. You expand over some combinatorial object called pipe dreams, and you can read off monomials that will generate your Schubert polynomial. Okay, so we have some rich combinatorics that's generating these Schubert polynomials. And another nice property is that they'll give us a z basis of the polynomial ring itself. Okay. So they're just a perfectly fine basis of our polynomial ring. And so when we study the product of two Schubert polynomials, we expand, and we'll get our familiar structure coefficients. So this is the same as this, is the same as this. So not only when we expand this product, we know that this should be an integer because these are an integral basis in our polynomial ring, but by the underlying geometry, we know that these are going to be non-negative integers because these are counting intersection points, as we saw over there. Okay. One other nice fact before we move on is right here, we know that we have this isomorphism. So of course, these should be our Schubert coefficients that we've been seeing reappearing. But one nice fact is we actually don't have to worry about computing modulo this ideal. We can actually compute this expansion on the level of the polynomials themselves. Okay. Any questions? Okay. So a central problem in the field is to find a manifestly positive combinatorial rule for these coefficients. Okay, we know that there are some non-negative integers. We can think that they're counting points. So they're counting something, but we would like some discrete combinatorial object such that there is no cancellation in our formula to write down this quantity. Okay. But we would like to maybe write down a more rigorous definition for what we're actually looking for here, because combinatorial rule, lots of people can have different opinions on what that is. And so for today, the framework that we'll be investigating this question under is looking for a sharp P rule for CUVW instead. Okay, so we want to be able to find a rule such that we can check a +1 contribution to our Schubert structure coefficient in polynomial time. Okay. So let's see. Oh, I could finish over here. So what we'll do now is, in general, this problem is entirely open, but let's chew on a special case and see if we can understand the complexity of the underlying problem in some special case, where we understand things a bit better. So let's look at the Grassmannian setting. So you can think about taking your complete flag variety and projecting to the Grassmannian, and that's going to give you a special case of the picture if you're more geometrically minded. And if you're more combinatorially minded, our Schubert polynomials are going to specialize to, in the case of Grassmannian permutations, they're going to give you Schur polynomials. And we understand quite a bit what are the structure constants of Schur polynomials. You see lambda mu nu. These are our Littlewood-Richardson coefficients. And so these are going to be the same as the structure coefficients for that special case of those particular, whatever those corresponding permutations would be. So lambda v mu w. Okay.
So the lambda, the w underscore lambda, is that supposed to mean the cycle type of w, or?
No, it's a bit more subtle,
Okay.
but I'll define it after if you want to see explicitly. But once we fix the symmetric group that's living in, it's a one-to-one. Yeah, so studying these Littlewood-Richardson coefficients is a special case of this greater problem that we've seen. Okay, and why we like the Littlewood-Richardson coefficients is they compute, maybe I do, let's start another board. So these Littlewood-Richardson coefficients, we know a sharp P rule for these. Okay, and so our Littlewood-Richardson coefficients, C lambda mu nu, is counting the number of semi-standard Young tableau. So by semi-standard Young tableau, I just mean integer fillings where I'm going to weakly increase as I'm reading left to right and strictly increase when I'm reading down a column. And I want these to have shape nu skew lambda. So here I'll have nu, and then here I'll have lambda with fillings mu here, subject to some ballot condition. Okay, it doesn't really matter what the ballot condition is. It's just saying if I read the entries in a particular way, I should read more ones than twos, twos than threes, threes than fours as I'm reading everything all the way through. Okay, so these are very explicit conditions that if I give you a tableau, in polynomial time, you can check that it's one of these that we want to count. So the Littlewood-Richardson rule gives a sharp P rule for our Littlewood-Richardson coefficients. Okay. As it turns out, if you
Question
Yes?
before you raise that equation that you have on top.
That I have on top.
Yeah, that one on the top of that part of the board. Why, naively speaking, why there is not a sharp P rule? That looks
Good
like
question.
I'm solving a system of
Good
polynomials.
question. Good question. So we can, and as we will see, we can write down what does it mean to be in this intersection as a system of equations. However, first, we have to generate some generic matrices. And there's no reason why there should exist generic matrices that have small entries. Second, it's not clear that whatever point you're going to try to plug in to check will be small. And so because of those two reasons, this, right, you could maybe try to troll someone and say that this is a combinatorial rule, but it's certainly not a sharp P rule unless there's some significant advances with regards to those two issues. But good thing to catch. Other questions? Okay, so, right, this gives a sharp P rule. And so far we've been talking mostly about counting complexity, but what about the decision problem for these Littlewood-Richardson coefficients? So how about deciding if C lambda mu nu is equal to 0? How hard should that really be? We have a very explicit combinatorial rule, so maybe that would help us. Okay. I know that it should be at least in NP because, again, I can tell that it's positive by you just handing me a tableau and I can check it. Okay. So the idea is we could take our semi-standard Young tableau of that type, let's say our LR tableau, and to that, I can characterize what it means to be a Littlewood-Richardson tableau in terms of satisfying a system of linear inequalities. Okay, and so a tableau T that we would want to check, we would want to recognize would be an integer point, or an integer solution here. And if we're satisfying a system of linear inequalities, it looks like we're building a polytope, and we exactly are. So this gives some polytope, P lambda mu nu, and an integer solution, or a tableau, is exactly corresponding to an integer point inside of this polytope. And so that decision problem is really asking, is there an integer point in this polytope? So easy. We just have to solve an integer linear programming problem, right? And I say that because, right, in general, this problem is NP hard. Okay, so we need some miracle to help us actually get something more efficient, and luckily we have one. So a theorem of De La Vera and McAllister as well as Momoli, Narayanan, and Sahoni, Momoli, we're actually going to have that deciding non-zeroness is n in the class P. You can do this in polynomial time. And how you can get past this integer linear programming issue is using via the saturation theorem of Knudsen-Tau. Okay, and so what the power of this theorem allows you to do, we're not going to get into the details, but it allows you to, rather than having to check if there's an integer point in this polytope, I just have to check if there's a rational vertex to the polytope. And by the structure of the equations, I just have to know if there's a point at all. I just have to test, using the saturation theorem, if there is any point in this polytope. And so you can use ellipsoid method, whatever your favorite program is, to get a polynomial time algorithm for this problem. Okay. And so not only is this polynomial time, it's polynomial time even if we are encoding our partitions in binary. So it's as efficient as we would expect. Questions? Okay. And so then the natural, we'll go back to our bigger picture. What about the complexity of these Schubert coefficients? Okay, we saw that the vanishing problem is as easy as it gets. But for this general counting problem, we don't have any combinatorial rules to rest on. Okay. So what do we do? What do we know? We do know that actually these Schubert structure coefficients are in this class gap P, which I didn't tell you what it is, but it's just the class that I can think of as being in sharp P minus another problem that's also in sharp P. Or in other words, I have some way that I can compute these Schubert structure coefficients by summing some positive number of things that I can check a +1 membership in polynomial time minus another set of objects in sharp P. Okay. Okay, and so this is, it was first noted by Alejandro Morales, which you can see from work of Postnikov and Stanley, and more recently in work of myself and Igor. So we have some signed formula for these, but that doesn't tell you much more about the complexity. You can use these to get maybe some asymptotic formulas, but it doesn't tell you quite so much about the vanishing. And the reason I say that is a very different problem, but also in the realm of algebra, we can look at the problem of trying to commute symmetric group characters. Okay? And this problem, also in gap P, but that decision problem of deciding if symmetric group characters are non-zero is not in the hierarchy at all. So things can get very bad with these decision problems. And having a however nice sign formula doesn't help. So we don't have so much intuition as to what we should expect from these things. Okay. So what about some partial results? Okay, so we have some work of Kevin Purbu, who showed us how to play some game with the roots of the while group to have some necessary condition on vanishing. Alan Knudsen has another necessary condition where you analyze the descents of the permutations, that's indexing our Schubert structure constant, and sometimes he's able to tell when we'll have vanishing. Billy Vakil use Eriksson-Linnesson's permutation arrays to say if I construct one of these arrays and it is not of the kind that I want, then I know that the Schubert structure constant should be 0. Saint-Dizier and Yang have a rule in terms of looking at polytopes. They say I can take the Minkowski sum of the Minkowski sum of the Newton polytopes associated to the Schubert polynomials for u and v, and see if there's a particular integer point that's missing, then I'll know that the Schubert structure constant should be 0. So we have a lot of necessary conditions, but no perfect combinatorial ways to actually detect this non-vanishing. Okay? And as far as I know, there's gaps. You can't just patch these conditions together and hope that this is going to cover the entire landscape. There are cases that are not necessarily covered by any of these. Okay, so our theorem, oh, this is exactly where I don't want it. Our theorem is exactly giving us an upper bound to the complexity of this problem. So deciding if CUVW is positive, or in other words, if this generic intersection of Schubert varieties is non-empty, this is going to be in the class AM, which I haven't told you what it is, but I will. It's going to be in the class AM, but we do have some assumptions, just one. We'll have to assume the generalized Riemann hypothesis. Okay, so this class AM is sitting between the first and second levels here. So not only do we know that this problem is in the polynomial hierarchy, if you allow me to assume GRH, so it's in the polynomial hierarchy, and moreover, it's rather low in the hierarchy. It's within the second level itself. Okay? And so our first corollary is that, firstly, it's in the hierarchy. Second corollary is that deciding this non-vanishing is actually going to be in NP, assuming, again, we'll need GRH, and something called strong de-randomization. Okay, so this is sort of a technical assumption in computer science where you might be more familiar with ordinary de-randomization. And this is the property that says if I have some algorithm that I can actually decide yes or no to a problem in polynomial time where I'm getting the question right most of the time, and I can sort of use some sense of randomness. If I can do that using randomness and getting things correct most of the time, then I can actually just do it in general. So that's the idea of de-randomization. This is the assumption that BPP is P. And so this is a non-deterministic version of this. So I'm going to sort of black box it for now. I didn't tell you formally what this class AM is. I'm more than happy to chat about it after the talk, but it might be a bit technical. But the idea is these are interactive proofs between a computer and an oracle. And so somehow between these conversations, your computer will be able to actually check that the answer is yes in polynomial time, getting the answer correct most of the time. Any questions?
Do you have a result when you just assume like Riemann hypothesis instead of the generalized version?
Stay tuned.
As in, it's already on a preprint, or it's?
No, I'm joking. So you can weaken the hypothesis a bit, but you have to have some technical assumption about prime numbers. So it can be weakened, but again, I think it would be too technical for us to make explicit at the moment. Okay, so I'm going to sort of sketch out the pieces that we're using, and hopefully you can get an idea how we would get to finding what AM is, why would this be a class that we would think of, and where is GRH factoring into all of this. Okay, so we'll highlight, this isn't going to be quite a proof, but this is going to be a sketch of the key ingredients, and we'll just sort of walk through what's going on. Okay, and so the key problem at play is something called HN. And the idea is we are going to slowly but surely reduce our problem to HN. We're going to say our problem, our Schubert problem, is actually a special case of this problem called HN that we already know the complexity of. And so that's going to be a reduction that we use to get this upper bound for the problem. Okay, so what is HN? So we'll take some polynomials, Fi, so some system of polynomials that should have integer coefficients. Okay, where I don't want these to have exponential in n degree, I don't want them to have exponentially many terms, and I don't want the coefficients to be exponentially large. Okay, and so HN asks if this system, Fi, equal to 0, this is going to be some system of equations, has a solution over C. Okay, so what is HN standing for? It's standing for the Hilbert-Nullstellensatz. So how hard is it to actually decide if this system is satisfiable? Well, before some more technology, we just had the weak Nullstellensatz at hand. And so what this says is we shouldn't have a solution over C if someone could hand me some polynomials gi such that when I'm taking this product, they'll all sum to the unit. Okay, so the certificate, what I'd have to check is someone from above would hand me these GIs, and I would check this. And this would give some check that's in P space, where P space is sitting outside of PH here. But with some extra technology, we can no longer be sitting on top of the, having to use the Nullstellensatz. This is a theorem of Koiron from 97, who proved that HN is in this class AM, this class of interactive proofs, assuming GRH. Okay. Yes.
To use this and talk about complexity, don't you need some bound for the degrees of G or something like that?
Exactly. So using very intuitive Grosvenor basis bounds, you can bound the degrees of G, and that gives you exactly that P space result. Okay, so where does GRH factor in here? So the idea is we want to bound sizes of two sets, where if our system was originally satisfiable versus if it was originally unsatisfiable, the sizes of these two sets are going to be very different. And our interactive protocol is going to be able to tell us the answer from that fact. And so the idea is if, let's say this is my system S, so if S is actually satisfiable over C, then I should have at least some number of B primes, it's going to be exponentially large, primes P, such that my system S is satisfiable over that finite field. And if unsatisfiable originally, then there would be no more than some other cardinality A primes P such that S is satisfiable over that finite field. Okay, so what this is saying is, if it was originally satisfiable, it's still going to be satisfiable at least for B primes. If it was originally unsatisfiable, things are only going to turn around in a nasty way at most A times when I'm checking satisfiability over that finite field. And most importantly, A and B have a difference in cardinality that's exponential. Okay. Now, GRH is hiding in getting this bound A. Okay, it's rather technical, but it's hiding precisely here. Okay. And so that's this problem.
Can you say anything in one sentence to those of us who heard that GRH is important our whole lives and couldn't survive around a square root if we had to explain it?
Could you repeat?
Why? Many of us, at least one of us,
Yes.
has heard GRH our whole lives and would not
Yes.
survive around a squid game if we had to explain why.
Yes.
Can you say why here?
Why here? Why is it important?
What's the deal?
It implies positivity of Schubert constants, so that is sufficient for you. I mean, again,
What does it get you? Why do we care where the zeros are? I mean,
Right. I mean, right here, it's telling us something very particular about this density of numbers coming from working in this finite field. It tells us about the density of solutions over a finite
they're
field.
more uniformly spread out. It's easier to get at them with less work. Is that the idea? That's the kind of explanation I'm looking for.
I don't know if I'll be able to give you what you're looking for.
That's a good answer.
But it's a good goal. You know, I can work to get there. But thank you. Okay. We can't actually reduce to HN itself. We're going to need something a bit more called HNP. And so this is going to be a variant of this HN problem, where my system S is going to be over these polynomials Fi, where rather than them having integral coefficients, there are going to be some monomials in parameters, AIs. Okay, and so this is HN parameterized. And so the idea is, so this is proven this summer by a group of computer scientists, El Mansour, Balaji, Nosan, Shiramohadami, and Worrell. And they prove that HNP is an AM assuming GRH, where HNP is asking if this is, if this equal to 0 is now satisfiable over C adjoin these parameters. Okay, so why do we need these parameters? It seems rather technical. But the idea is that whenever we were looking at this generic intersection that we were building, right, the whole issue is that we don't have necessarily small candidates for what are these generic coefficients here. And so what we'll do instead is say, I'm never going to evaluate them to anything at all. I'm just going to keep them as formal parameters and look for a solution over where I've actually just formally adjoined these parameters. And so I'm not going to have to worry about the generic issue at all. Okay, and it goes forward rather straightforwardly. You can reduce this problem to GRH, or not GRH, to HN. Okay, and then the last ingredient, just finishing up, is how do we get a system of equations that is capturing this Schubert intersection? And I don't think I'll write them down, but you can Nick Hine and Frank Sotilli have specified a system of bilinear equations that solutions of the system are exactly in correspondence with solutions to the Schubert problem. So they've written down a rather explicit system of only bilinear equations. And not only are they bilinear, they actually have a square system. So equal number of equations and variables. So it's sort of the most efficient that you would hope for one of these ways to write down this problem. And so we can just appeal to the equations that they've already written down for us. This is, I think, in 2017. And then by using our trick of not evaluating our coefficients to be anything, we just have to solve their system over this algebraic extension, which reduces to HNP, and so we're all done. Okay, and I'll end with, we started this story by talking about the complete flag variety. And if you are interested in algebraic combinatorics, this is sort of the type A situation. You might ask, what was special about this being type A? And the answer is almost nothing. So with Igor and myself, we have that, deciding these coefficients, where this is A, B, type A, B, or C structure constant. This is in deciding positivity is in AM, assuming GRH. And if you feel sad about type D with David Spire, we get the result for type D as well. And I'll stop there. Thanks.